Hello everyone, this is Manisha Mishra, Assistant Professor in Mathematics, Applied Science Department at St. Andrews Institute of Technology and Management, Gurgaon. This college is affiliated to Maharishi Dayanand University, Rohtak. Right, so today I will discuss the topic method of separation of variables. Right, so in method of separation of variables, I will discuss heat equation and wave equation. Right, so first we will see that we will see the topic classification of PD, right? So because after classification you will know about heat equation, wave equation, Laplace equation, right? So first, classification of PD. So in classification of PD, that means you have a PDE and how you will classify your PDE. So a second order partial differential equation, A del 2u upon del x2 plus B del 2u upon del x del y plus C del 2u upon del y2 plus D del u upon del x plus E del u upon del y plus fu plus G is equal to 0. So this is your partial differential equation of second order, and we always do classification only for the second order PDE, right? So this PDE can be classified into three equations, but there is a condition here. So first condition is, we can see that this is your coefficient of A, this coefficient of B, that means that 2u upon del x del y coefficient, and we know the notations that you can write it capital R, small r, or capital, whatever you want to write here, and this S, this is your T, this is your P, Q, and U and G, right? So this is your equation 1. So there is a condition here that this equation is said to be elliptic if this condition b square minus 4ac is less than 0. If this condition is satisfied, then we can say that this equation is an elliptic equation. Parabolic, when it will become parameter parabolic, then if b square minus 4ac is equal to 0, condition will satisfied. When hyperbolic, if b square minus 4ac is greater than 0, that means if these three conditions are satisfied, then we can say that our equation is classified into elliptic, parabolic and hyperbolic, right? Or in between, or, right? So classify the PD this equation comparing. So first one, this is your heat equation. So what we have, this is the heat equation. I will discuss each and every part in our next videos, and today I will discuss also these parts here, points here. So classify the PD. Del u by del t is equal to del 2u upon del x2. So we don't know what is this PD, right? So to know about this PD, first we will compare this equation with our first equation. So what will we have if you compare this equation with this one? Then you can see that A is equal to 1, B is 0, C is 0, E is equal to minus 1, D, E, F, G. There is no role of D, E, F, G, but we need to calculate B, A, B, C. So find B square minus 4AC. So you can see that B is 0. So 0 minus 4 into 0, that means 0. The given PD is parabolic. We can say that which one condition is satisfied. Second condition is satisfied, and second condition is parabolic. So our PD is parabolic, right? Now classify the PD. Del 2u upon del x2 plus del 2u upon del y2 is equal to 0. So again we can see here that comparing the given PD with equation 1, so A is equal to 1, B is equal to 0, C is equal to 1. Now find b square minus 4ac. So 0 minus 4 into 1 into 1, so minus 4 less than 0. So we can say that which condition is satisfied? Condition 1 is satisfied because minus 4 is less than 0. So this is your elliptic, right? This is your Laplace equation. And classify the PD. Del 2u upon del x2 plus 3 this one plus del 2u upon del t2 is equal to 0. So find ABC from here. So A is equal to 1, B is equal to 3, C is equal to 1. Find B square minus 4AC. So 9 minus 4 is equal to 5 is greater than 0. So our given PD is hyperbolic. That means for the classification, we have to learn only three conditions: elliptic, parabolic, and hyperbolic, right? If your PD is elliptic, that means this is your Laplace equation. This condition is Laplace equation. This is your Laplace equation. If PD is Laplace equation, then we can say it is also elliptic. If your PD is parabolic, then it will be heat equation. This is your heat equation. Heat equation condition. And if your PD is hyperbolic, then this is your wave equation, right? So we have our all our three conditions and also three examples here. Now, next, what is wave equation, what is heat equation, and what is Laplace equation? These, and also boundary in your syllabus, boundary conditions, and write all equations with boundary conditions. So initial and boundary conditions are there, and also equations are here. So first equation is wave equation. So wave equation means del 2y upon del t square is equal to c square del 2y upon del x2. This is your wave equation. This is your wave equation, right? So here double time derivative with respect to x, double time derivative with respect to t, and here y depends on x and t. So y is a dependent variable, x and t are independent variable, and I told you that in PD can be more than one independent variable, right? So y is a function of x and t. So del 2y upon del t2 is equal to c square del 2y upon del x2. Now, what is initial and what is boundary conditions? So boundary conditions are y at 0 and t. That means x is equal to 0 and t is equal to 0. That means y at x is equal to 0 is 0. Y at x is equal to L is equal to 0. Y at x 0 is equal to fx. This is your boundary condition, right? What is initial condition? Derivative of y at t is equal to 0 is equal to 0, and 0 is less than x less than L. That means, you know, wave equation, that means it moves like spring. We can take example like a spring. If you string a spring, then you can say that it moves like a wave, right? So we are considering the length of the wave is L. That means the wave is moving 0 to L. 0 is the origin and L is the length of the wave, and t is the time. So our wave is moving in time t as the length L. Conditions are, these are the boundary condition. At x is equal to 0, our solution will be 0. At x is equal to L and t is equal to t, our solution is 0. At t is equal to 0, our solution is a function here. And initial condition is derivative of y at t is equal to 0 is 0. 0 is less than x less than L, right? So this is your wave equation condition in with initial and boundary condition. Can we ask 2.5 marks question is in your final semester exam? Yes, so classify this equation with bound initial and boundary condition. So you can classify this equation, right? And your wave equation always a hyperbolic equation. That means it will satisfy b square minus 4ac is greater than 0 condition always. You can check here. This is your exercise. Then you will check all these three equations, that which one is hyperbolic, which one is parabolic, and which one is elliptic, right? Now, heat equation. So what is your heat equation? Del u upon del t is equal to c square del 2u upon del x2, right? So you can see that u is differentiating one time partially with respect to t, and here u is differentiating two times partially with respect to x, and this is called one dimensional heat equation. This is your one dimensional heat equation. U is a dependent function, x and t are independent function. That means solution of u will depends on x and t here. Now, where the boundary conditions? So u at x is equal to 0 is equal to 0. U at x is equal to L is equal to 0. And the initial condition is u x0 is equal to fx. Right? So also we can see that at time t is equal to 0, our solution is fx here. Right? So third condition is Laplace equation in two dimensional. So Laplace equation in two dimensional. So Laplace, we have already known Laplace, that double derivative of partial derivative of u or whatever your dependent variable is. So Laplace equation in two dimensional is del 2u upon del x2 plus del 2u upon del y2 is equal to 0, and 0 is less than x less than l, and 0 is less than t 0 is less than y is less than by L. So u at x is equal to 0, y is equal to u is equal to 0, and that means all the three conditions are boundary conditions. First one, at x is equal to 0, your solution will be 0. At x is equal to L, your solution will be 0, and at y is equal to 0, your solution also be 0. And initial condition is u at x is equal to x, y is equal to a is equal to sine n pi x upon L here, right? So this is your Laplace equation, and with your Laplace equation you can check from here that I told you that this is your Laplace equation and this equation is your elliptic equation, right? So we have our all the three conditions equations with initial and boundary conditions. So guys, just learn these conditions with initial and boundary conditions, right? These equation with initial and boundary conditions, right? Now I think, okay. Now, our next method is methods of separation of variables. This question can be 7.5 marks question. So, or 15 if it is lengthy, it's depend on the conditions. So, methods of separation of variables. So, we here the term separation. That means if you have variables, so you can you you will do, you just separate these variables into different variables and just find the solutions, right? So in this method we assume that the dependent variable in the product is the product of two functions. Dependent variable, that means if u is a dependent variable, x and t are independent variable, that means u is a solution of x and t, I told you. So each of which involve only one of the independent variable. So u here dependent variable, x and t are independent variable. So our solution will be u is equal to x into t, where x is a function of x and t is a function of t. Here, wave equation. This is your wave equation. So y is a dependent variable. That means we can write y x and t. That means y is a function of x and t here, right? So our solution will be y is equal to x into t. There we are writing the dependent variable is the product of the two independent variables, right? So our solution will also depends on these conditions. So there is an example here. So using the method of separation of variables, solve del u by del x is equal to 2 del u upon del t plus u, right? So this is your first order PD. We can see that order is 1 here. So this is your first order PD, and to solve this PD by the method of separation. So first, let u is equal to xx into tt. That means we will use same procedure in each and every question. So just guys, learn carefully. Let u is equal to x into t. Why we are taking x? Because u is a function of x and t. So capital X is a function of small x, capital T is a function of small t. So u is equal to x into t is a solution where capital X is a function of small x and capital T is a function of small t only, right? Now u is equal to x into t, so we need to calculate del u by del x and del u by del t, so that we will put all these value in equation 1. So just calculate del u by del x, so differentiating with respect to x. So del u by del x, you can write x differentiation will be x dash into t. So this is your partial differentiation. So t will treat like a constant, and del u upon del t. So x will be constant. So x into t dash. Right now, from equation 1, write all these value here. So x dash t is equal to 2x t dash plus xt. Now to just two or more three lines to for the calculation. So x dash t is equal to 2t dash plus t of x, means x is common. Then separate these terms, separation in separation of method, separate these terms. So separation means x variable will be one sided and t variable will be another side. So x dash upon x is equal to 2t dash plus t upon t is equal to k here, right? So this is your separation, right? So we are here separate these variables, so it is called separation of variables, right? Now we are taking these two separate terms is equal to a constant k, where k is a constant, right? Now next we will consider x dash upon x is equal to k, as equal to our constant, and 2t dash plus t upon t is equal to k, right? Now we will solve these two variables separately. So on integrating both sides, so x dash upon x, that means log x, and kx plus log c. Dx integration will be x, and the dx upon x integration will be log x, and we will consider a constant log c because our solution is in log, so we can take constant log c here, and log c is your integrating constant. So log x is equal to kx plus log c. Log c you can write here, so log m minus log n, log m by n. So log x upon c is equal to kx, right? Now x is equal to x by c is equal to, if log will be, if log is removing it from here, then it will be e to the power kx. So our solution x is equal to c into e to the power kx, right? And as I told you that x is a function of a small x, so we can see here that we are getting x is as in small x, right? Now for the solution of t, so 2t dash plus t upon t is equal to k. So just dividing by t, so k minus 1 plus 1 here. So just move from right hand side. So t dash upon t is equal to k minus 1 upon 2. Now on integrating both sides, so dt upon d is equal to k minus 1 upon 2 integration small t dt plus log d. Log d is your integrating constant. So log capital T is equal to k minus 1 upon 2 into t plus log d. So log t and log m minus n again, and t is equal to d into e to the power k minus 1 upon 2 into t, right? So we can see that we small x, capital X is a function of a small x, capital T is a function of a small t. That means we are getting our solution. So put the value of x and t in equation 2. So what is equation 2? Equation 2 is here u is equal to x into t. So just write all these values in equation 2. So you can see that u is equal to c into e to the power kx into d e to the power k minus 1 upon 2 into t, right? This is your equation third. Now one condition is given in your question, that where ux0 is equal to 6 into e to the power minus 3x, right? So we have to use this condition because this condition is given to us. So okay, ux0 is equal to 6 into e to the power minus 3x. So just write here, so u is equal to c into e to the power kx d into this one, t here 0. You can see that t means 0 here, right? And x same as it is equal to 6 e to the power minus 3x. Just watch your condition carefully, because don't confuse here, because uxt, that means u is a solution of x and t here, so t is here 0, so just write t here 0, e to the power 0 1. So c into d e to the power kx is equal to 6 e to the power minus 3x. Now on comparing both sides, then c into d is equal to 6 and k is equal to minus 3. Just write these value in equation third, and we are getting our solution here, right? In each and every question we will follow the same method here, right? There will be no change. But if this is your first order condition, so first order condition is different, but in second order condition, I am going to discuss second order partial differential equation. for the method of separation, right? So that condition will be changed. Now let's see. Use the method of separation of variables to solve the heat equation. This is your heat equation. As I told you that this is your heat equation and this is your boundary and initial condition here, right? And this condition is given in your final semester exam questions. Maybe if it comes, right? So del 2v upon del x2 is equal to del v upon del t. This condition is given here. Let us assume that we are solving this equation by the method of separation. So our method of separation, v is equal to x into t, where x is a function of x only and t is the t only, right? Now v is equal to xt. This is your second equation. We need to calculate del v upon del t and del 2v upon del x2. So del 2v upon del x2 will be x double derivative of x into t, and del v upon del t is equal to x single derivative of t here. Now put all these value in equation 1. So write all these value here. So you can see that x double derivative t is equal to x t single derivative. Now separate these terms. So x double derivative upon x is equal to derivative of t upon t is equal to k. K is a constant, right? Now again write this equation is equal to this one and this equation to the k, another constant k. So x double dash is equal to kx. We can write it x double derivative minus kx is equal to 0 and t dash upon t is equal to k, right? Our next target is to find the solution x and t. So t dash upon t, now we are taking t dash upon t is equal to k. So integrating on both sides, so integration t dash upon t is equal to k dt plus log c, and on integrating both sides, so log t is equal to k into t plus log c, and log m minus log n again, so t upon c is equal to e to the power kt, or t is equal to c into e to the power kt here. This is your solution for the t, right? Now x double derivative minus kx is equal to 0. So we will apply here three cases. First one, k is equal to negative integer. Second one, k will be positive integer, and third one, k is equal to 0. And cos x and sin x are the periodic function. So we will follow this solution only for the periodic function, right? So only k is equal to minus p square. I am taking only k is equal to minus p square case here, because only in this case I will get periodic functions, right? And I will show you in our next video session that for the case k is equal to 0 and for the case positive integer, right? So the x double derivative minus kx is equal to 0. So condition case 1 is when k is equal to negative integer, that means minus p square, right? So just write here minus p square. So double derivative of x plus p square x is equal to 0. So this is your differential equation. And to solve this differential equation, auxiliary equation will be m square plus p square is equal to 0. M square is equal to minus p square. M is equal to plus minus iota p. And we can write this equation because roots are imaginary. So x is equal to c1 cos px plus c2 sin px, right? So this is your differential equation solution. Now v is equal to total up solution is v is equal to c1 cos px plus c2 sin px into t is c into e to the power kt, right? Now k is your minus p square, so just write here minus p square. Now initial conditions and boundary conditions are given. Condition is given when x is equal to 0, your v is also 0. So just write here x is equal to 0. So 0 is equal to c1 cos 0 plus c2 sin 0 e to the power minus p square t. So sin 0 0, so it will be c1, and c is here also c1 c e to the power minus p square t. So these two c into e to the power minus p square does not never be 0. So our constant will be 0, because if we are taking this 0, that means our solution will be 0, right? And our solution is not 0 only at x is equal to 0, only at x is equal to L, right? So c1 is equal to 0, right? Now from third, put C1 here 0. So V is equal to C into C2 sine Px into e to the power minus P square T, right? This is your equation 4. Now again condition is given. We have our conditions. When V is equal to 0, at x is equal to 0, and at x is equal to L, V is equal to 0. So just apply. At x is equal to L, our V is 0. So right here, 0 is equal to CC2 sine PL e to the power minus P square T. So again, we can see here that our this constant is not equal to 0, because if constant is equal to 0, that means our solution will be 0, right? If our constant C into this is equal to 0, that means our solution will be 0. So only sine PL is equal to 0, only sine PL will be 0, and sine PL is equal to sine n pi, because at n pi sine always gives 0 value. So PL is equal to n pi and P is equal to n pi upon L, where n is any integer, right? Now from the equation 4, just write all these values. So V is equal to, we are considering C2 is equal to new constant C3 sine n pi x upon L into this one, and we are considering Bn is equal to C3 new constant. We can replace constant by each and everything, so just don't worry about it. So V is equal to Bn sine n pi x upon L into e to the power this one, right? This is your final solution for the for the heat equation and by the method of separation of variables. I will share two or more three examples related to separation of variables in a wave equation and also in Laplace equation, right? So thank you.